Sound travels through gases, liquids, and solids at considerably different speeds due to the nature of the interactions of the molecules in the different media. Near room temperature, the speed of sound in air is 343 meters per second, or 767 miles per hour, and is markedly greater in liquids and solids. For example, sound travels more than 4 times faster in water and more than 17 times faster in steel than it does in air. In general, sound travels slowest in gases, faster in liquids, and fastest in solids. Like the speed of a wave on a guitar string, the speed of sound depends on the properties of the medium. In a gas, it is only when molecules collide that the condensations and rarefactions of a sound wave can move from place to place. It is reasonable, then, to expect the speed of sound in a gas to have the same order of magnitude as the average molecular speed between collisions. For an ideal gas, this average speed is the translational root mean square, or RMS, speed given by equation 14.6, where VRMS equals the square root of 3 kT divided by m, where T is the Kelvin temperature, m is the mass of a molecule, and K is Boltzmann's constant. Although the expression for VRMS overestimates the speed of sound, it does give the correct dependence on Kelvin temperature and particle mass. Careful analysis shows that the speed of sound in an ideal gas is given by V equals the square root of gamma kT divided by m, where gamma equals Cp divided by Cv is the ratio of the specific heat capacity at constant pressure, Cp, to the specific heat capacity at constant volume, Cv. The values of the speed of sound in various gases are given in the table. The factor gamma was introduced in section 15.5, where the adiabatic compression and expansion of an ideal gas are discussed. In section 15.6, it is shown that gamma equals 5/3 for ideal monatomic gases and has a value of 7/5 for ideal diatomic gases. The value of gamma appears in our equation for the velocity of sound in a gas because the condensation and rarefactions of a sound wave are formed by adiabatic compressions and expansions of the gas. The regions that are compressed become slightly warmed, and the regions that are expanded become slightly cooled. However, no appreciable heat flows from a condensation to an adjacent rarefaction because the distance between the two, half a wavelength, is relatively large for most audible sound waves, and a gas is a poor thermal conductor. Thus, the compression and expansion process is adiabatic. In a liquid, the speed of sound depends on the density ρ and the adiabatic bulk modulus BAD of the liquid according to V equals the square root of B adiabatic divided by ρ. The bulk modulus was introduced in section 10.7 in a discussion of the volume deformation of liquids and solids. There it is tacitly assumed that the temperature remains constant while the volume of the material changes. That is, the compression or expansion is isothermal. However, the condensations and rarefactions in a sound wave occur under adiabatic rather than isothermal conditions. Thus, the adiabatic bulk modulus, BAD, must be used when calculating the speed of sound in liquids. The table gives some data for the speed of sound in liquids. In seawater, for instance, the speed is 1,522 meters per second, which is more than 4 times as great as the speed in air. The speed of sound is an important parameter in the measurement of distance, such as in sonar. When sound travels through a long, slender, solid bar, the speed of sound depends on the properties of the medium according to V equals the square root of y divided by ρ, where y is Young's modulus and ρ is the density. The table lists the speed of sound in some example solids. In summary, the speed of sound in a gas is given by V equals the square root of gamma kT divided by m, where m is the mass of a molecule, T is the temperature, K is Boltzmann's constant, and gamma equal to Cp divided by Cv is the ratio of the specific heat capacities at constant pressure and constant volume. The speed of sound in a liquid is given by V equals the square root of BAD divided by ρ, where BAD is the adiabatic bulk modulus of the liquid and ρ is the density. Finally, the speed of sound in a solid is given by V equals the square root of y divided by ρ, where y is Young's modulus and ρ is the density.